Welcome to class, everybody. I think I noticed a decline in the quality of this particular page in our Zoom when I did the gallery view. So I'm going to do the gallery view for a minute to say hi to everybody, and then we're going to revert back to a non-gallery view. I think it's reducing my bandwidth a little bit, and I think it's making the video a little bit less visible. Of course, class notes are posted, so that's not such a huge problem. But anyway, let's see who's here in the room. Ronnie's here. Marcus is here. Hi, everybody. Kendall's here. Danny's here. Hi, Danny. Nick is here. Good to see you. Eric's here. Edwin, good to see you. Yay. Brianna's here. Zane, hi. Gabriel's here. Stephen's here. Khadijah's here. And is it Serindy here? Is it Serindy? Srinidi?
Yes, yeah, that's me.
Which one?
It's Nidhi Adi Abadi.
Nidhi. Okay, great. Welcome, everybody. Hey, we got a fun lecture today. We're going to talk about circuits. We're going to draw some circuits. And this is really where the rubber meets the road. The sort of abstract stuff with true, false becomes quite real when we are using actual wires and circuits. So I've got a raised hand. Nick, I see a raised hand. Got a question?
Sorry, I think you have the wrong notes up. I think it's for a different class for on the blackboard.
Oh, really? Do I have like 265 linear algebra notes up?
Yeah.
Oh, hey, extra credit. Thank you for letting me know. I'll fix that right after class.
All right, thank you.
I'm so sorry about that. Holy cow, how did that happen? All right, well, we'll get that fixed. Thank you so much. Yeah, I'm struggling. I'm trying to juggle as many classes as you are, and I'm not a young chick anymore. So thank you. I need all the help I can get. All right, so you got your graded work back if you turned it in. Were you able to view your graded work okay? I mean, it was a silly little homework. It was on time management and sort of, an Easter egg hunt through our resources, right? But the next homework you should have uploaded now, right? And that was more of a mathy homework. So the next graded homework, special homework, will go up either tonight or in the morning, and it's going to cover the material that we cover today, and it's also going to cover material from our lecture coming up on Wednesday. So just be on the lookout for that. I'll shoot out an announcement when that's posted. By the way, I did send out an announcement saying that I have started posting worksheets, because somebody in one of the classes said, hey, I'd like just some worksheets. And of course, exercises at the end of each section in the ebook provide extra practice, but worksheets are also good. And since I create the worksheets, they're worded more like the kinds of questions you'll see on the test. So worksheets are up, and I will continue to post worksheets as time permits. Okay. Thank you so much for that heads up. All right, so let's pin this and go back to speaker view. And so tonight we are going to talk about circuits, and there's a triangle relationship, folks, between circuits and Boolean expressions and IO tables. Who knows what IO means? Anybody? Just mic right in or chat in. I'll look at the chat.
I need to get a job. Input, output?
Yes. Input, output, exactly. So IO tables look a lot like truth tables, but they're going to be a little bit easier, and you'll see that. Boolean expressions look a lot like statement forms. They're going to involve P's, Q's, R's, ands, ors, nots. The only big difference is we're going to use uppercase letters instead of lowercase letters in general when we are looking at Boolean expressions. And binary addition is something that we're working our way up to, because you see, circuits if they're going to be useful, have to actually do something. And so by the end of the lecture on Wednesday night, you should be able to build a circuit that will actually add binary numbers, okay? So we're going to kind of sneak up on that tonight by just learning the basics of circuit design and how to draw them and how to find any one of these from any of the others. So given a circuit, we'd like to be able to find the Boolean expression and the IO table. Given the IO table, we want to be able to find the circuit and the Boolean expression. You get the drift. We want to be able to just traverse this little graph fluently. And then there's a very special form for a Boolean expression, and it's called Disjunctive Normal Form. And that's real useful. In general, any kind of normal form has two qualities. It's universal. That means any Boolean expression should be able to be transformed into a logically equivalent expression in disjunctive normal form for this application of normal form. So it's got to be universal. It also needs to be really useful. Like, why would we have a normal form? It needs to be useful. So we're going to be looking at those. Meanwhile, let's just quickly do our do now. I'm sure everybody in here knows how to do this, but I just want to make sure because I had a couple of students who seemed not quite clear on how to make the setup for a truth table that has 3 input variables. And so what we do is we realize 2 choices for P, it's true or false, times 2 choices for Q, it's true or false, times 2 choices for R, that's also true or false, for a grand total of 2 cubed or 8 rows. And under P, we write true, 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 just split 8 in half, right? So 4 trues followed by 4 falses. And you've noticed this probably in WebAssign. It sort of sets you up and does it for you, but you need to be able to do this on your own. Under Q, we split 4 in half, and that's 2. So 2 trues followed by 2 falses. Repeat until you fill the column. And finally, we split 2 in half and get 1. So it's every other. So under the last variable, it always alternates. And we always start with true. We also always put the variables in alphabetical order. This is a normal form because it's useful. It's useful because when we all set up our truth table like this, then we're all looking at the same columns later on. It's also useful because when you set up your truth table like this for an 8-row situation, you're never going to accidentally miss a row or repeat rows. And it's universal. You can always set your truth table up this way. So it's kind of a silly example of a normal form. All right, so let's get started with circuit design. A couple of basic things that we need to know. We're in section 2.4, of course. True is now going to be denoted by the binary digit 1. Okay, I might write it like this, or I might just write a stick 1. And you want to interpret that as representing what we would consider a hot wire. Hot in the sense that that wire has juice flowing through it. It's got electricity flowing through it. As opposed to false, which is going to be represented by the binary digit O. And when we see that on a wire, or if a wire is carrying the value O, we are to understand that that wire has no electricity running through it. It's literally a cold wire. And so speaking of wires, well, in the plane, you can prove in graph theory that there are lots of graphs that cannot be drawn unless the edges, in this case wires, cross in the plane. So if you just see this, then the wires are not touching. We understand that to mean, yeah, it looks like they're crossing each other, but you know, they're actually not touching, okay? As opposed to seeing this where there's something called literally a solder dot. If you've ever done any soldering with a soldering iron and a solder wire and solder wick to kind of soak up the leftover solder, this is called a solder dot. And when we see 2 lines crossing with this dot, it means, hey, they are touching. They're carrying the same value. They're either both cold or both hot. Okay, so that's something to understand just from the get-go. All right, so the idea of a circuit, folks. I don't like that pen. Let me get a black. I have a black one right there. Looks black, that's green. The idea of a circuit. We can think of it as a black box. If we can't see the innards, if we can't see the inside, we could still see what's feeding into it. So I'm using uppercase letters, and these are inputs. These are input wires, P, Q, and R, okay? And then there's a box. We just consider this like a black box. It's even called a black box. Something's going on in there. There's a circuit in there. And then that black box acts on these inputs, and then there's an output. And there can be more than one output. But in the most basic case, we have these inputs, P, Q, and R, and then these, the inputs are these wires. And then the output is S. And it'll be hot or cold. In other words, it'll have true or false on it. And if you ever built a circuit, maybe in high school, a lot of times the way that we know that our circuit is doing what it's supposed to do is there's actually like a little light bulb that lights up if the output is hot. So one of the ways that we talk about the output being a hot output or true or a 1 is we say that the circuit lights up. So it lights up if the output is hot. In other words, S is 1, okay? Which is true. Okay. Right, so we have gates. And these gates work like the logical operators. We just draw pictures of them. So let's look at the gates that are involved in circuit design. We have 3 of them, one for and, one for or, and one for not, just like in logic land. So the and gate, now I'm going to first draw it with 2 inputs, P and Q. Okay, it looks like a capital letter D that's been stepped on, so it's kind of smashed flat. And then we put and in there. So P and Q are being input into the and. And the IO table that's associated with the and gate is just like the truth table for the and operated statement. If we have P and Q, then P and Q, it's going to have 4 rows, just like a truth table, but instead of trues and falses, we're going to put 1s and O's. So under P, we would write 1, 1, 0, 0 for true, true, false, false. And under Q, we would write 1, 0, 1, 0. And this AND gate operates just like the AND operator in logic, statement land. It's 1, 0, 0, 0. So it's just what you think it should be. We also are going to have an OR gate. So we can draw it with 2 inputs, P and Q, and it looks a little different. It's got a kind of a point to it, but we just write the name inside the gate in case your drawing, isn't, perfectly clear. Everybody knows it's an OR gate because we write OR inside the gate. And its IO table looks just like what you think it should. Again, under P, it's 1, 1, 0, 0. Under Q, it's 1, 0, 1, 0. And this is the inclusive OR, so it's almost always true. P or Q is evaluated as 1, 1, 1, 0. Questions? It's just what you think it should be. Then there's the NOT gate. And the NOT gate just takes 1 input wire because the NOT operator is the unary operator. Now the NOT gate looks a little different from the and OR because it's got like this Rudolph nose. So you actually don't have to write NOT inside the NOT gate. But think about it. These wires actually carry juice or they don't. And the purpose of the NOT gate is to flip the bit. What could go wrong if we tried to feed two wires into a NOT gate? What could possibly go wrong? Hi, Mariama. Hi, Matthew. Hi, Gabriel. Looking for you here. I don't see you. Anybody? Any idea what could go bad if we tried to feed two wires into a NOT gate? Think about it. The job of the NOT gate is to flip the bit. In other words, if a hot wire comes in, we want a cold wire to be the output. All right. If a cold wire is being input, we want the output to be a hot wire. We want it to flip the bit. Let's say there were two wires going into a NOT gate. What would the NOT gate output if those two wires had different states? Like what if we put a hot wire through it at the same time as a cold wire? The NOT gate would not know how to evaluate that. You see what I'm saying? So one of the mistakes that about 8% of the class is going to make when you draw a circuit is you're going to be feeding more than one wire into a NOT gate. And I'm trying to tell you right now, that's not going to work out because the NOT operator is a unary operator, not a binary operator. You with me? And of course, the IO table for the NOT is just what we think it is. It's got two rows and it just flips the bit. Now, it turns out that although I have drawn the AND and the OR gates having two input wires, we are allowed to have as many input wires as we want to the AND and the OR gates because they're very simple. The way that these gates work are really simple. The AND gate only lights up the circuit. In other words, the output is only hot if all the inputs are hot, right? That's the way AND works. The OR gate only outputs hot output. Well, it outputs hot output if any of these inputs are hot or all of them, right? So we have this situation where it's called fan in K. Fan in because when you draw an AND gate with a bunch of wires coming into it, it kind of looks like a fan of wires coming in, and that's perfectly legal. You could put in P1 and you could put in P2, ... up to K input wires. That is perfectly legal for AND. Same with OR. You can input a bunch of wires to an OR gate, and there's nothing wrong with doing that. In fact, it's very efficient. It can be fan in K as well. Now, kind of a word to the wise. I have drawn these with slight, at a slight angle coming into the OR gate, but we generally draw our wires perfectly horizontally or vertically just because they're, these diagrams are easier to read. All right, so armed with this information, we have AND gates, OR gates, and NOT gates. They look like this, or they could be fan in K if they're AND or OR gates. And we have the idea of wires that cross but don't touch and wires that do touch with a solder dot. Let's go right into this game and let's learn to draw a circuit given a Boolean expression. We're going to learn by doing. It's super easy. It's kind of fun. So example 1, part A. Let's draw the circuit associated with this Boolean expression. And it's going to look familiar. It's going to look like a statement form, but it's going to have capital letters. All right, here we go. Open parentheses, P and Q, close parentheses, or open parentheses, P and not R. Super simple. First thing we do is we realize, hey, we are trying to play the game where we are given a Boolean expression and we're trying to get the circuit. So we're trying to go this way in our diagram. Scan the Boolean expression. Check out how many variables there are. We have a P, we have a Q, we have an R. So we're going to need 3 input wires. and I'm going to space them out a little bit. P, and I'm going to make this wire a little bit long because we're going to do something else in a minute. Q, I'm going to skip a space between my inputs, R. Okay. So we always draw our circuits left to right because we read left to right. I mean, if we were in Saudi Arabia, we'd probably draw them right to left, but we're here and we're reading left to right. So we put our inputs in, coming in the left. You never have more than one input wire for a particular variable. If we need another P wire, we're just going to pull off of this P wire, okay? And we're going to split it with a solder dot. And we are going to do that in a minute, okay? So we know that we will work inside parentheses first. We understand that much about statement forms, and the same rule applies for Boolean expressions. So we're going to need to build an AND gate and AND together the P and the Q wire. And then in parallel, we're going to build an AND gate that's going to take P and not R. That means we're going to have to build a NOT gate for the R. Then after we've built these two AND gates, the output wires are going to get ORed together. We're going to run them through an OR gate. Does that make sense? So there are a lot of ways to draw these. The main thing is just try to keep it as neat as you can so that the poor fool that's trying to read it can read it. So I'm just going to bend the Q wire up. I don't need a solder dot to bend a wire. It's perfectly legal to bend a wire. I'm just getting them close enough that I can run them through an AND gate without that AND gate being too big. But again, you know, we're not going to be too particular. If your AND gate's bigger than my AND gate, nobody cares. Now, that is the P and Q gate right there. In preparation for building the AND gate for P and not R, we need a not R. So we're going to go ahead and run the R wire through a not gate. And again, you don't have to write not in there. I'll just go ahead and do it for thoroughness, but that little nose tells us, hey, that's definitely a not gate. It can't be really confused with an AND gate or an OR gate. So we need to get the P wire down here close to this not R wire. See, this wire is not R. So I'm going to solder here and I'm going to pull it down. I'm just going to stay out of my own way. I'm not going to cross this wire through a gate. Then I'm going to bend it. And it's, you know, okay, my AND gate's going to be a little bigger. It doesn't really matter. And there is my output wire from that AND gate. So this is P and not R. Everybody with me? Questions? Good to see everybody. All right, so now we just want to finish this up by realizing that we need to OR together the outputs from these two AND gates. So we can just bend these wires, no solder dot needed for bending wires again. And we're going to run this through an OR gate. And it's kind of misshapen, no problem. Just write the word OR in there. Close enough, full credit. Okay. So that's how we would build a circuit given a Boolean expression. And we're going to do another one tonight. I just wanted to kind of start off with something simple. Lots of ways to do this, folks. I could have said, okay, I need a P wire, and we could have bent it here, you know, and put the AND gate a little bit shifted up. That, you know, and that P wire could have been above the not R. It doesn't matter. There are lots of ways to do this. Okay, so we want that whole triangle at our disposal. We really want to be able to get from a circuit to now the IO table, or the Boolean expression to the IO table. So we've got the circuit now, and now we're going to draw the IO table. So that's part B. Construct the IO table for this circuit. And I'm going to show you how to do it if you don't have the Boolean expression. If all you have is the circuit, and that is one of the games in WebAssign, okay? We're going to have a column for P and Q and R. You don't have to write this above it. I'm just putting it in here for the sake of the notes to remind you, hey, these are our inputs. Okay. And we're going to have, of course, 8 rows because, you know, we can mix and match hot and cold. So under P, 1111, 0000, under Q, 1100, 1100, and under R, 10101010. Our job is to find the right values to put in the output column, which is the column we call S. S is usually reserved for output, but not always. Okay, so this is the game. I'm going to use colored pens, and we're going to figure out what happens for each of these rows. Now listen, understand this. Each row of the I/O table describes what we call an input state. In other words, it gives us a complete description of the input. In other words, when we have a 1 under P and a 1 under Q and a 1 under R, which is what's happening in row 1, we understand that that means, hey, P is a hot wire, Q is a hot wire, and R is a hot wire in this row. It's a complete description of what's going on for the inputs. So I'm going to use red up here, and I'm going to put a 1 and a 1 and a 1 because we're going to evaluate what happens in this row 1 when all the inputs are hot wires. Okay? So we execute the AND operator just the way that we saw in the page before. It's the AND operator. 1 is like true. So if we run P is 1 and Q is 1 through this AND, what comes out on this wire? Anybody? So it's 1 and 1, or true and true, if you want to think about it.
So true, 1.
Yep, it sure is. It's going to be a 1 there. Fantastic. Now, let's look at what's happening down here, because we can't evaluate the OR. Well, actually, we've got a 1 there. We know the OR is going to be a 1, don't we? But let's go ahead and be thorough. Let's run this 1, which is the value of R, through this NOT gate. What's going to be on this wire? What's the output from the NOT gate?
0.
Yep, it sure is. It's going to flip the bit from 1 to O. Great. All right. And the value on this P wire is the same as it was here because these are connecting. So there's a 1 here. All right. So now we're going to AND together O and 1. What should that be?
0.
That's right, because true ANDed with false is still false. So this is a cold output. And now we run the 1 with the O through an OR gate. What's the output?
1.
1. Everybody following that? So that means the output in this first situation, we got 8 different switches here, okay? But in this first situation, for this input state, the output is hot. All right, let's take a look at row 2. I'll do that in green. All right, P is hot, so we'll put a 1 for P. Q is 1, so we got a 1 there, and R is O now. All right, let's evaluate that. When we run P is 1 and Q is 1 through the AND, what's the output? Somebody else maybe.
1.
Sure, 1 and 1 is certainly 1. So we got a 1 up here. All right, great. Now we have an O on this R wire, and we're going to run that through the NOT gate. What's going to come out?
1.
Absolutely. And the P is a 1, so we have a 1 here. See, we're just tracing this through. Now, what's the output from this AND gate? When we feed in this green 1 and this green 1?
1.
Of course, it's a 1. And that means the OR is going to output a 1 because we're feeding 2 1s in, and that's more than enough to make that 1 come out as the hot wire output. So that means in row 2, we also have an output of 1. It's kind of fun. Let's do another one. Let's do 2 more, and then you can finish it later, okay? All right, here I'll use the blue pen. P is 1, Q is O, and R is 1. All right, so when we AND together, P is 1 and Q is O, what comes out, folks?
0.
Yep, because true and false is false. Nice. When we run the R equals 1 through the NOT gate, what comes out?
0,
Mm-hmm. And P is a 1, so that's what's down here. Now we're running O through an AND with a 1. So O and 1 is
O,
great. Now we're going to run O through an OR gate with another O. What comes out there?
O,
And this is the first time we've seen a cold output for this circuit, so that's an O there. All right, we'll do one more. P is 1, Q is O, R is O. We AND together 1 and O, we get an O. Flip the bit, the O switches to a 1. P is 1. 1 and 1 is 1. AND together O. Wait a minute, I think I made a mistake. 1, O, O. 1 and O is O. No, I didn't. O or 1. What is that going to be?
1,
1.
Great. So that's another hot output. So the way that's the way you can find the IO table directly from the circuit. You've got to run all, there's 8 more, there's 4 more for a total of 8, possibilities. So you finish this later.
I have a question.
Sure.
So when you have the O for R and it goes through the NOT, why does it turn into 1?
Because that's the job of the NOT gate. It flips the bit.
Oh, okay. Oh, okay.
Okay. That's its job. Is it just changes the value to the other value.
Okay.
And that's why we can only feed one value into a NOT gate, because it wouldn't know what to do if we fed in 2 different values at the same time. All right, so now that's a chore. That's time consuming, and boy, wouldn't it be nice if there was an easier way to build an IO table. Do you agree? This is time consuming. It's doable, but not exactly how we want to spend our time. So hence, hopefully, the motivation for what we call disjunctive normal form. Disjunctive normal form is a Boolean expression that lends itself to direct translation to an IO table. Let me show you what I mean. Example 2. Consider this Boolean expression. And it's going to be kind of long, so I'm going to make sure I start all the way over here at the left. All right, I'm going to skip a line because I want to label these components in a minute. All right, so I'll open a parentheses. In the first parentheses, we have P and Q and R. Now we're going to OR that with another component, open parentheses, P and Q and not R. Or, big or, open parentheses again, not P and Q and not R. Close parentheses. Or, here's our last component, not P and not Q and not R. Okay. So we have 4 components. These parenthetic expressions are called components because they're all being ORed together. Folks, this is an example of disjunctive normal form. Every Boolean expression can be converted to a logically equivalent Boolean expression in disjunctive normal form. It can be quite a chore to do that, and I'm going to forego that exercise with you, but it can be done. But here's why it's so useful. Notice that inside the parentheses, we have a complete description of the input states. What do I mean? Okay, let's look inside component 1. It says P and Q and R. Now, when we just say P, folks, when we just state P, we are saying P is true. So this first component says, hey, P is true, and Q is true, and R is true. In other words, this situation says all three input wires are going to be hot. And this whole expression says if this happens, or this happens, or this happens, or this happens, we want hot output. The Boolean expression tells us when we want to get hot output. This first component says, hey, we're going to want hot output if all the inputs are hot, because that's what P and Q and R means. When we look at the second component, it says, hey, P and Q and not R. We're describing what's true, okay? This says P is 1 and Q is 1 and not R is 1. It means P is hot and Q is hot and R is cold, because not R is what's 1. That means R must be O. See what I'm saying? So this is a complete description of the input. It says, hey, if the input is that P is hot and Q is hot and R is not hot, we want the circuit to light up. We want an output of 1. Or if P is cold and Q is hot and R is cold, we want hot output. Or if all of the input wires are cold, in other words, not P is what's 1 and not Q is what's 1 and not R is what's 1, which means P and Q and R are all O, we want a hot output in that instance. So it describes 4 different times we want hot output. And this can directly be translated into the I/O table. So that's part A. We're going to construct the I/O table directly from the Boolean expression. And the reason it's just so nice is because we can write our I/O table. We know we've got 3 variables coming as input, so we'll need 8 rows as usual. And we just set it up as usual, 1, 1, 1, 1, 0, 0, 0. Gosh, I'm always missing that 8th row. O. And then under Q, 1, 1, 0, 0, 1, 1, 0, 0. And under R, 1, 0, 1, 0, 1, 0, 1, 0. Okay. And now we're going to be able to read directly from these possible input situations when we want a 1. So just to expound, each row is a complete description of a possible input state. Input state is the state of all the input wires as taken as a whole. For example, in row 1, it says P is hot and Q is hot and R is hot. And so we write that as P and Q and R. In row 2, P is hot and Q is hot, but R is cold. So that means and not R is hot, you see? So this is a description of what's happening in row 2 as far as the input state is concerned. We can do that for every single row. Oops. So let's do that. Let's just label these rows with their appropriate input states. For example, what would go in row 3? What's a description of that input state? Anybody?
P and not Q and R.
Perfect. Everybody see it? P is hot and Q is not. That means not Q is and R. We always write what is true. And then, of course, it's P and not Q and not R for row 4. And I will shut up and I'm going to fill this out and you can fill it out on your paper at the same time and you can check. Does that make sense, folks? And it's super easy now. We don't have to run those values. We don't have to build the circuit first and run the values through, which is so time consuming. We can read directly from this Boolean expression where the ones go. We want hot output if P and Q and R. In other words, we want hot output in row 1 because that's where P and Q and R are all hot. We also want hot output if P and Q and not R. That's row 2. We want hot output if not P and Q and not R. Which row is that?
6.
That's right. Or if it's not P and not Q and not R, we want hot output in that instance. What row would that be?
8.
Exactly. So we put 1. See, disjunctive normal form is great because it gives us a complete description of what's going on with the input. That way we can identify precisely the rows where we have a 1 or a hot output. Then there are O's everywhere else. We just put O's everywhere else. I'm using different colors, but of course you can use the same color. It doesn't matter. Now, again, just to emphasize the difference between what the and means versus the or in this expression. You see, inside parentheses, this is all happening at the same time. P is hot at the same time that Q is hot and R is hot. See, this is the row P and Q and R. And this is the row P and Q and not R. Inside a row, this is all happening at the same time, and that information gets anded together. But different rows cannot happen at the same time. We can't have P and Q and R all being hot at the same time that P and Q are hot and R is cold, you see? So the row 1 input can't happen at the same time as row 2 input. They happen separately. But this says we want a hot output if what's going on in row 1 is what the input situation is, or if row 2, or if row 6, or if everything's cold coming in, which is what row 8 is talking about. So we have ands across the row, and then we or these together to get the Boolean expression. So we have just learned 2 things at one time, folks. We have just learned that if we have the Boolean expression given to us in disjunctive normal form, we can go directly to the IO table. But let's say we didn't have the Boolean expression. Let's say that you were just given the IO table. Well, now you know that you OR together the input states from the rows that yielded a hot output. You see what I'm saying? So we've just learned to go back and forth between IO table and Boolean expression when that Boolean expression is in disjunctive normal form. So of course, this wouldn't be complete unless we were asked to draw the circuit. We need practice with drawing circuits. So let's draw the circuit associated with these. Okay. So, I mean, we can see it from the Boolean expressions written here in the IO table. We don't even need to see the Boolean expression right now because we know that we're going to have AND gates to AND together P and Q and R, and we're going to have an AND gate to AND together P and Q and not R, and we're going to have an AND gate fan in 3 because we're going to feed in a not P and a Q and a not R. We'll have a big old AND gate for not P and not Q and not R, and then at the end we're going to OR them all together. The OR gate's going to be fan in 4 because we'll have an output wire from each of these 4 AND gates. And those 4 wires can feed into the same OR gate because OR can accept more than 2 wires. All right, so when we draw this, I'm going to give myself plenty of room. I'm going to skip several lines between my inputs, and I'm going to put these inputs in alphabetical order. Now, when we start drawing circuits for adders and half adders, we may not put them in alphabetical order, but there's no reason not to here. All right, so let's take a look. We need an AND gate that's going to have P and Q and R wires as input. We're going to input P and Q and R into an AND. So I'm just going to pull this P wire over a little bit, and then I'm going to bend the Q wire up And I also need the R wire, all right? So I'm gonna bend the R wire and bring it up here. And I'm gonna make this a little longer because I know something's gonna happen, you see, because some of these are gonna have NOT gates first that have to be executed before we can feed the wires into the AND gates. So I'm gonna want a little room kind of in here to build the NOT gates where I'm gonna need them. But here's the AND gate for what we were calling expression 1 in the original Boolean expression. That's here. And there's the output wire. And in a little while, it's going to feed through an OR gate with these other output wires from these AND gates. All right. So now, when I just kind of scan what's going on, this next expression is going to be an AND gate where P wire and the Q wire and a NOT R feed through as input. But I'm noticing that all the other expressions have NOT R. None of them use R again. So I'm going to go ahead now and I'm going to solder here because I need to understand that these two are touching. And I'm going to run R through a NOT gate. Okay? And I'm going to be able to pull from that NOT gate. Like I'm going to back it up a little bit. I'm going to back this up a little bit. So there's my NOT R. So I want to feed P and Q and NOT R through an AND gate. So I have a P wire here. I'm going to pull from this P wire and just bend it. It can cross these wires. It's not touching them. This is the P wire. I have a Q wire right here. So I'm going to solder from that and pull it over here. And now I have the NOT R wire here. So I'm going to solder from it and pull this up here and just bend it. I don't need to solder when I'm bending. And that is going to feed into the second AND gate. And there's the AND expression from row 2. You can just check it. You can kind of run it backwards and make sure that what we're feeding in is actually P and Q and not R. Everybody with me? And now we've got to build an AND gate that accepts not P and Q and not R. So we're going to need a not P gate. So here's P right here. I'm going to pull from P and bring it up here and bend it and run that through a NOT gate. So this is my NOT P wire. I already have the NOT R wire. So it can just stay right there. And I need a Q wire. There's different places to take the Q wire. I could take it from here and run it down here, but this is also Q right here. I can take it from here and I could run it right there, but I'm going to actually run it in between just to kind of clean that up a little bit. So we've got Q ANDed with not P, ANDed with not R, and that's expression 3. Everybody with me? And then finally, we need everything knotted. Well, we've got a not Q right, we've got a not P right here. We've got a not R wire right here. What we don't have yet is a not Q. So I'm going to pull from Q and go ahead and bring it down below and line its knot up here. I kind of like to line things up. You don't have to. Don't worry about it. But there's my not Q wire. And we've already got the R that's knotted here. So I'm just going to pull from that. And now we got to figure out how to pull the not P down. And this is getting crowded. See, this is the not P wire. So, but there is just enough room to pull from that. And I'll just pull it down here. And now I can run those through an AND. You don't want things to get too crowded. Like if this got too crowded, I could back this NOT gate up a little bit to give myself a little more room. See what I'm saying? Like we don't want this wire to touch that solder dot. So if it looks like it's getting too close, right? Whiteout is really important, or an eraser. We cannot have wires touching that we don't want to have touching. You don't want things running into each other. It's got to be big enough that you can really see what's going on. So we've got the AND gates built for the 4 components. And now I'm just going to bend these wires and get them close enough together that my OR gate doesn't have to be too big. And of course, you write and OR inside your AND gates and your OR gates in case, you know, they don't look perfect. But something like this. And this is even slightly different than what's in the notes, but, you know, you'll see that, you know, this is the idea. There's more than one way to do this, but this is the basic. I think I've tried to get it mostly the same. Questions? So let's just think about what we have learned how to do so far, because remember, our goal is sort of this, this triangle where we can get from any of these to any of the other ones, okay? We started with a Boolean expression, we drew a circuit. And then we've also now gotten an IO table and a Boolean, from a Boolean, we've gotten an IO table. But we know we can go from the IO table to the Boolean because of this disjunctive normal form, okay? So the last thing to do is if we're presented with a circuit, we'd like to be able to get the Boolean expression. We know if we're given a circuit, we can run the values through and get the IO table. We've done that. But what we haven't done is circuit to Boolean expression. And that's real easy. Let me show you how to do that with our third example. Any questions before we go to that next example? Okay, great. Find the Boolean expression associated with this circuit. So I am going to draw the circuit. Before I do, we already know that if we have a circuit, we are capable of running the values through it and building an IO table. We know from an IO table, we can get the Boolean expression, but I don't want to do all that work. I'd like to build the Boolean expression directly from the circuit. So this circuit's going to have 3 inputs, P, Q, and R. Okay. I'm going to draw from the Q wire, bring it up close to the P wire, and I'm going to run those through an OR gate. I'm going to make this just long enough that I can write something on it, this piece of wire here. And then that's going to get run through a NOT gate. Now this Q wire, I'm going to run through a NOT gate. I'm going to hang on to that for a minute. I'm going to draw from P, bring it down close to R, and run P through an AND gate with R. Now we're going to knot together. Excuse me, we can't knot those together, can we? We're going to OR together those. So the NOT Q is going to get ORed together with the P and R. And finally, these 2 outputs from the NOT gate up top and this OR gate at the bottom are going to be sent through a final OR gate for the output S. Okay, so that's our circuit. So it's super easy. We're just going to basically read through the circuit and write down the expressions that are coming out of these gates. So let's just start at the top. This is an OR gate. We're feeding in P and we're feeding in Q. So the output from that OR gate is the expression P or Q. That's simple. Then that expression gets run through a NOT. So that means the NOT is getting applied to P or Q. So this is now not the quantity P or Q on this wire. Does that make sense? Great. All right, let's look at what's happening in this middle wire here. What's sitting on this output wire? What would be the Boolean expression right here? Anybody?
Zero.
Well, we don't know the value that Q has, so we
Oh,
don't know
not
that
not Q.
it's whatever not Q is. Great. All right, what about this wire? I'm sort of working serially here. In parallel here. What about this wire down here that's coming out of this AND gate? What's on this output wire?
P and
P
R.
and R.
Yes, P ANDed with R. Excellent. So now we can figure out what's on this output wire, this coming out of this OR. I'll just point to it because we're kind of running out of room. This is not Q getting ORed with, we got to use parentheses, P and R, okay? Now it doesn't matter what order we put these because and OR are symmetric operators. So you could write this P and R is the same thing as R and P, right? And that ORed with not Q. See what I'm saying? There's a couple different correct ways to do this. Like both of these mean the same thing. But the point is, it's a not Q getting ORed with a P and R, no matter how you write it. I generally, write things in alphabetical order, but not always. Now, our final answer is the output from this wire, that's on this wire up here, the wire to S. So let's write our final answer here where we have enough room. Can you write the final answer? The final Boolean expression? Well, it's not the quantity P or Q getting ORed with, now open parentheses, I'll write the not Q or P and R version. Now you might look at this and you may realize, hey, we got more parentheses here than we actually need. We actually don't need these parentheses. It's not wrong to have them, but it's an OR operator here and an OR operator here. So, we do need the parentheses here because that has a not being applied to it. So we can't lift these parentheses because then this not wouldn't be getting distributed properly. But we actually don't need these parentheses. But it doesn't hurt to write them. See, De Morgan's law tells us if we want to get rid of these parentheses, this OR would flip to an AND, you see, and then we need parentheses around not P and not Q because we would be trying to OR that AND operated expression, with this. So you might as well just leave it like this. So that's the way you can find the Boolean directly from the circuit. You don't have to build the IO table first, but if you're building the IO table anyway, then that's a natural segue to the Boolean expression, which would of course be in disjunctive normal form. This is not disjunctive normal form, but it's equivalent to disjunctive normal form. It would take some steps and it would take some logical equivalences to get there. Questions? Now, I want us to just start thinking ahead to what we're going to be doing Wednesday, because you see, this is all still kind of theoretical. What are we doing with this? Why? Well, the bottom line, folks, is we actually want to build something. We want to be able to build a computer that does, some operation. And the simplest operation to start with is binary addition. We can build a circuit that will add binary numbers. Let me show you how to start that thought process. All right, in the binary digits, okay, we have two of them. It's 0 and 1. By the way, we usually call it O instead of 0, okay? It's no big deal. So when we think about binary addition, the simplest case of binary addition would be if we're just taking two single digit binary numbers and adding them together. So we're just going to think first about adding two single digits, where those digits are the binary numbers 0 or 1. Once we learn to do that, we're going to, that's what we're going to start with on Wednesday. We're going to build a circuit that does that work. Then we can start building circuits that add multi-digit, long binary numbers, and lots of them. So let's just think about adding two binary digits. There are 4 situations, okay? Because if we're adding 2 digits, the digits could both be O, they could both be 1, or one could be an O and the other could be a 1. So we're going to think about it this way. It could be that we're adding O plus O. It could be that we're adding O plus 1. It could be that we're adding 1 plus O, or it could be that we're adding 1 plus 1. So let's just talk about these simple examples using what we know about numbers like O, or what we call 0. See, in the decimal system, we have 10 digits, O through 9. By the way, O through 9, the way that we write them, we're using Arabic digits because mathematics was actually lost to Europe during the Dark Ages and was preserved in the Middle East. And actually, the Middle Eastern mathematicians got a lot of really interesting results while math was dead in Europe. Those results and the number system, which is the number system we use, O through 9, was brought back into Europe during, heaven forbid, the Crusades. So we owe a lot to the Middle Eastern mathematicians who preserved and expanded higher mathematics while Europe was, in the middle of the Little Ice Age and the plague. All right, just a little history for you. All right, if we are adding 0 plus 0 or O plus O, what do we want to get? I don't care what number system you're in, base 10 or base 2 or base 8. What do you want to get if you add 0 plus 0 or O plus O?
Zero.
Having a corporate.
Okay, I heard a vote for 0, but somebody else is talking. Would you say that again? All right. Well, the point is, yeah, I mean, in any world, nothing plus nothing is nothing. We want to get an O for the answer, okay? No matter what number system we're playing in. Now, we also understand that O is not supposed to add any value, right? When you're adding O to your checking account, you're not increasing your balance, right? And we want that to be preserved. We want O to have that property where it's the additive identity, where X plus O is always X, okay? So when we add O plus 1, what do we want to get? In any world, what would we want to be getting? We want to get, we want to get 1, right? If we add nothing to O, nothing to 1, we want to still have 1. Now, here's an interesting thing. When we add O to 1, do we want to get the same thing that we get when we add 1 to O? Do we want addition to care what order we add the same 2 digits?
No.
Yeah, we don't want these to be different. So we want to get a 1 when we add 1 plus O. So we're kind of just going on just sort of basic ideas about adding, this is called commutativity, X plus Y equals Y plus X, and the fact that 0 has some properties that we want to preserve. Now here we are, and we want to add 1 plus 1 in binary. Now, if we said that 1 plus 1 was O, then we'd be saying 1 plus 1 is the same thing as O plus O. Do we want that? Do we want the value of 1 plus 1 to be the same as the value of O plus O? No, we don't. Do we want 1
No.
plus 1? Yeah, we don't want it to be the same thing, because I mean, then suddenly, if 1 plus 1 was O, then, you know, we would never be able to get past 1, you know, in our number system. It would always reset to O every time we got to 2. In the same spirit, we don't want O plus 1 to be the same as 1 plus 1, because in some sense, we want 1 plus 1 to represent something different than O plus 1. Somehow it's got to be bigger, right? So this is where, just like, you know, I'll just do a little over here on the side, you know, if we have 9 plus 1, we don't want this to equal O or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8. Or even 9, we want it to be something that we haven't seen yet, and that's when we have to have another digits place. We have to carry, you see? So now we need a carry. So we do reset to O in the ones place, but we add a second digit to the left, and that's called our carry. This digit on the right is called the sum digit. This digit is called the carry. Okay? Now, we want everything to kind of be the same, no matter whether we're adding O plus O or O plus 1 or 1 plus O or 1 plus 1. In other words, we kind of want the computer to be outputting the same kind of information, at least in format, if not value. That means if we need a carry and a sum digit for 1 plus 1, we better build the machine that it outputs a carry digit and a sum digit. That means we have to rethink what's going on with these first 3, because they only have the sum digit, this digit in the rightmost column. But listen, if you have an odometer, you know, on your car, and, you know, an odometer goes up to like 999,999, like the standard odometer. If you have 12,000 miles on your odometer, well, there's a 0 sitting right there, and it doesn't bother us, because we know a 0 on the left doesn't add any value. That's a whole different ball game than putting a 0 on the right. Suddenly your car's got 120,000 miles on it, and that's very different from 12,000 miles, right? But in the same spirit of an odometer, where it doesn't hurt or change the value of a number to put zeros on the left, it's not going to hurt us one whit to go ahead and make this carry digit an O. It doesn't change the value. See what I'm saying? And once we have things sort of normalized like that, where we realize, okay, if we add 2 binary digits, we're going to get 2 output digits. One is called the carry, one is called the sum. The sum is in what we call the ones column. And because this is base 2, this carry is in the 2s column, not the 10s column. And so what we really want to do then is think about building a computer, a circuit that will output the correct carry and the correct sum. So this is the first time that we're going to see a circuit that has 2 outputs. It's going to have 2 output wires. One is going to be labeled the carry, and one output wire is going to be labeled the sum. So I want you to think about this before our next lecture. You actually have everything that you need to build this thing. I want you just to think about how you would build it. Think about building a circuit on 2 inputs. These are our binary digits that we're going to be adding. Call them P and Q, with 2 outputs, C and S, the carry and the sum, that correctly calculates this: P plus Q equals carry sum. Here, P and Q are binary digits. They're O's or 1s. We are going to build this thing on Wednesday, but you can think about it ahead of time. And we're just going to use ands and ors and nots. And it's okay in the circuit to have 2 output wires, okay? And we're going to try to do it efficiently. But the deal is, once we can add 2 binary digits, then it's going to be just a little short hop and skip jump to be able to add 3 binary digits. And then we can add anything at all. We can add 100-digit binary numbers together with lots of other multi-digit binary numbers. And these circuits that do this job are called half adders. This thing that I'm challenging you to try to figure out how to build is called a half adder. And from it, we will build a full adder. Because once you have a little circuit built, you can use it in other circuits. Just the same way when you write code and you write a module that does something, you can call that module in lots of other programs and you don't ever have to write it again, right? So once we have built a circuit that adds 2 binary digits, we can use that circuit along with any other gates we need like ands and ors and nots to build a circuit called a full adder that will add 3 binary digits. Once we can do that, we can add anything. So I just want to motivate you that, yeah, this is really where the rubber meets the road. It's not all silliness. This is what computers actually do. Any questions? Answers? Meaning of life? I could use that answer about right now. Okay, so tonight or probably tomorrow morning, I'll get that next special homework up. And again, it's going to have some problems on circuits, just the stuff that we've done tonight, but it's also going to have a problem where you're going to be leaning on what we learned Wednesday. So you won't be able to, work it all before the lecture Wednesday. By the way, we've talked about statement forms being logically equivalent, right? Like they might look different, but when we build their I'm going at IO table, their truth tables, their columns look the same, right? The same idea can be applied to circuits. So let me ask you this. If you were in circuit manufacturing and you could build a circuit using 3 gates, 3 inputs, but it only needed 3 gates. And the IO table for that circuit looked exactly the same. In other words, the output column looked exactly the same as a circuit that you built using 7 gates. Which circuit are you going to build? See, when those input columns, that output column, when they're identical, that means those circuits do exactly the same thing on the same inputs. Obviously, you're going to build the circuit that only uses the materials and labor with 3 gates. There are lots of ways to measure circuit efficiency, but one of the basic ways to measure circuit efficiency is by counting the number of gates in the circuit. And 2 circuits are logically equivalent if they have the same IO table and the same number of inputs. So that's one of the things that's going to pop up in this next special homework. I'm going to give you the definition of what logically equivalent circuits are, and then I'm going to ask you to figure out if a couple of different circuits are logically equivalent, and that's just going to boil down to looking at their IO tables and comparing them. If they are logically equivalent, then the natural next question is, which circuit would you actually want to use if you had to build it, manufacture it, produce it, that sort of thing. All right, so special homeworks are going to start to include new definitions and concepts that you sort of think about and learn on your own. That's a sneak preview. All right, so check out all the nice worksheets that I've started to stick into the good stuff folder. Some of them, I think all the ones that I put up there so far have solution sets so that if you need extra practice, you can start to get extra practice and you can bring those questions to office hours. My apologies to people that did come to office hour last night. I did get into the office hour last night. I fell asleep yesterday. I woke up like 8:30. So anyway, you can always request a special office hour if you need one that's earlier than Wednesday or Sunday. I've been giving people extensions. Yeah.
Yeah, I got one.
I can't hear you. I'm sorry, you're breaking up. Still can't hear you. You want to chat it in? Hossein, are we going to talk after class? Is that what you're trying to tell me? Man, something's going on with your mic. Okay, I'm going to stick around. I'll stop the recording, but then if I think a couple of people were having some trouble navigating WebAssign, and I'm going to stick around and help people out. All right. That's it from my end. Anybody else got any comments, questions, suggestions? I'll be sure and put up the correct class notes. I'm so sorry about that. Okay. Class dismissed. Have a great night. Enjoy this lovely fall evening. Everything is perfect.